me. And today I will speak about topological defects in the multi-axion system. So the title is a bit too long, but I will talk about topological defects of axions. And this is based on the works in collaboration with Jun-Sok Lee, my graduate student at Tohoku, and Kai Murai, a postdoc, and Wen In, faculty at Tokyo Metropolitan University. Okay, so as everybody knows, the QCD axion is a pseudo-Nabu-Gordon boson that appears when PQ symmetry gets spontaneously broken. So for instance, in the case of a single PQ scalar model with Mexican hot-type potential, at the very high temperatures, the potential looks like this, and the origin is stabilized, and the PQ symmetry is restored. But as the universe expands, temperature decreases, then at a certain point, the origin becomes unstable, and the PQ scalar field acquires non-zero depth. Then the axion appears along the phase direction. And if the U1 PQ symmetry were an exact symmetry, the axion would be massless. Okay. On the other hand, the radial degrees of freedom, which is sometimes called the axion, has a mass much heavier than the QCD axion. Okay. And this QCD axion was originally introduced to solve the strong CP problem of QCD. Namely, in principle, you could add this parity and CP violating operators into the Lagrangian of QCD with a coefficient of order unity. But this theta parameter, the coefficient of this operator, is constrained to be less than about 10 to minus 10 due to the neutron EDM experiment. So why theta parameter is so small is a strong CP problem. And the idea of the PQ mechanism is to promote the theta parameter to a field, the axion field, here if the decay constant, so that the axion acquires potential from this interaction to gluons, so that it is stabilized at the point where the CP is restored, or the effective theta parameter vanishes. So whatever theta parameter originally is, the axion is stabilized in such a way that it cancels the contribution of the theta parameter. And this is how the PQ mechanism solves the strong CP problem. And the dynamics or cosmology of the QCD axion can be broadly classified into two cases. One is the so-called pre-inflationary scenario, where the axiom already exists because U1 PQ symmetry is already broken during inflation, and it also acquires quantum fluctuations leading to the isocurvature perturbation. The other scenario is that the post-inflationary scenario, where U1 PQ symmetry gets spontaneously broken after inflation, so that there's no axion during inflation, so there's no isocurvature problem. And but associated with this U1 breaking after inflation, the cosmic strings are formed. And cosmic string is a line-like object, here shown by this green line. And in the real space, if you go around the cosmic string like this, then in the internal space or in the field space, the axion field changes by 2 pi if you go around the circle, the bottom of the potential minimum. Okay, and if you have potential, say coming from the interaction to QCD, then the axion acquires mass, and if the domain number is greater than unity, then say it is n, then as you go around the circle, you go up and down n times. So it means that in the real space, as you go around the cosmic string, you encounter n domain walls. Okay? And this domain wall number is quite important. And this evolution of the cosmic strings and domain walls have been extensively studied because they are crucial for estimating the axion abundance. For instance, I took this figure from the Bushman et al. This paper. These yellowish lines are the axion strings. Okay? And the blue regions represents the axion energy density. And this red box corresponds to the Hubble volume. And if the average number of cosmic strings contained in the Hubble volume is constant, the such string network is said to follow the so-called scaling solution. Okay. And it has been pointed out by several groups that there might be slight deviation from the scaling solution, namely the average number of cosmic strings contained in the Hubble volume might increase logarithmically as time goes. Although the increase is very mild, it's just logarithmic increase because in the realistic situation, there's a huge hierarchy in the mass scales, namely the decay constant and the axial mass. So in order to apply the numerical results to the realistic case, you have to rely on the huge extrapolation of the results. So this logarithmic increase results in the relatively large uncertainty in the prediction of the axial masses. And here I show the evolution of axion strings and axion domain walls in the case of domain wall number equals unity. So there's a unique vacuum in this case. Then, so this white lines are cosmic strings, and this bluish area are domain walls. And when domain walls appear, they are bounded by cosmic strings, and because of the tension domain walls, the string wall network shrink and collapse and disappear, okay, and producing a large amount of axions. And this evolution of cosmic strings and domain walls is very important to study how much axions are produced from this, the decay of topological defects. And here I summarize the current situation of the predicted axion mass. And as you can see, in the very old days, there's large uncertainty, but as time goes, the uncertainty sometimes becomes bigger. But if you look at most recent ones, the uncertainty shrinks a bit. And although there are some inconsistency or tension between different authors, but all of them seem to suggest the axion mass around 0.1 million electron volt or around 1 electron volt to explain all dark matter by the axions produced by the topological defects. And this is the current situation. But here I'd like to emphasize that all the numerical simulations shown here are based on the same setup. Namely, all of them assume a single PQ scalar model with a Mexican hat type potential. And so here the phi is a PQ scalar field, and it develops a VEV, FA. S is the rate of degrees of freedom, the axiom. The axiom appears in the exponent like this. And the reason why all of them assume the same the PQ model is that this is the minimal model. The number of degrees of freedom is a minimal in this case. So that's why they are adapted. They all adopted the same model. But it is fair to say that we know nothing about the PQ sector. Okay, we do not know the symmetry breaking scale. We do not know how do your PQ symmetry gets broken, and so on. So I believe it is worth studying what happens if you consider slightly more complicated case, say the model that contains multiple PQ scalars. So we may consider, so I'm saying that we should consider a different UV completion of the QCD axion, simply because we do not know the details of the PQ sector. But you might think that why do we care about the UV completion? Because, we are interested in the same low energy effective theory that contains the QCD axion, and that's it. So even if you consider more complicated the UV completion, it means that you have more, say, axions, so which have very heavy masses, and also heavy axions much heavier than the QCD axion. So as long as you are interested in relatively low energy phenomena, we may simply integrate them out, and then we have the same low energy physics. So why do we care about UV completion? But topological defects are kind of time capsule. So it contains important information on the very high energy scale, namely the symmetry breaking scale and also the symmetry breaking pattern. So it is important to study the UV completion. But you must still think that because we're considering now the field theoretic axions, so somewhere in the field space, you always have a point where all the symmetries are restored. And in the low energy, we have the spontaneous broken or PQ symmetry and the QCD axion. So whatever UV physics you might consider, there is always a field configuration that corresponds to the ordinary cosmic string of the QCD axion. In other words, the details of the UV physics may be contained in the string core. So here, maybe string core has some more complicated structure like this. It's a couple of strings connected by domain walls and so on. But if so, why do we care about UV physics? Because they're contained in the string core. If you look at the cosmic strings at a distance, it's just ordinary cosmic strings. You cannot tell the difference from the ordinary cosmic strings as long as the typical energy is much lower than the inverse of the string core radius. Then they evolve completely in the same way as the ordinary cosmic string. Why do we care about UV physics? Well, that is exactly the question I just asked, namely, is UV physics always confined in the string core? That is a question. And as you might expect, the answer is no. So let me explain why this is the case. So to see this, let us consider a minimal extended PQ scalar model. Namely, we introduced two PQ scalars instead of one. So we have phi1 and phi2, okay, capital phi1 and capital phi2, and both of them develop non-zero wave, f1 and f2, and the axions phi1 and phi2 appear in their exponent like this. For later use, I also introduced a normalized axion field or angles, theta1 and theta2, normalized by their decay constant like this.
Excuse me.
Yes,
Yeah, I'm not very, I don't know much about this axion physics. So very naive question is, so you assume here two Goldstone boson, right?
right.
So do they have coming from the same symmetry or coming from a different symmetry or?
Yeah, you could consider the various cases.
Hmm?
For instance,
Sorry?
yeah, for instance, here I did not specify the origin of phi1 or phi2 and how they get how get their depth.
Mm,
So
mm,
you may consider phi1. You have simply two different scalars, phi1 or phi2.
mm,
Or if you further if you consider another UV completion, which may
mm,
uh phi1, phi2 may be unified into a larger representation. That is also possible.
mm.
But here I've just considered two PQ scalars. We don't care about further UV completion.
And you can increase the number of phi I as many as you like.
Yeah, if you like, if you wish, of course, you could consider three PQ scalars, four PQ scalars, but as a first step, let us consider the minimally extended PQ.
Okay. Okay,
Yeah.
thank you.
So if you wish, of course, you could consider very complicated setup with n axions with like the clockwork axion model. But let me focus on this relatively simple setup. And because we introduced two scalars, we have two axions. But in the low energy, what we want is the QCD axion, and the other axion should be much heavy. So we introduce potential V1 to give a mass to one combination of phi1 and phi2 like this. So lambda is a dynamical scale that determines potential height, and N1 and N2 are anomaly coefficients, and they are integer numbers. Okay. And due to this potential, this combination of phi1 and phi2 becomes massive, and the orthogonal direction remains massless. And if we want to apply this model to the QCD axion, we want to identify the remaining almost massless direction with the QCD axion. And to mimic the contribution from the QCD non-positive QCD effects, we introduce V2. If we apply this model to the QCD axiom, this V2 should come from the interaction to gluons. So lambda prime is roughly given by the QCD scale, or the pion mass times the pion decay constant. And here N1 prime and N2 prime are different anomaly coefficients, and they are also integer numbers. And because we want the heavy axiom much heavier than the QCD axiom, we assume hierarchy between lambda and lambda prime. So V1 is much larger potential than the V2 potential. So for the moment, we focus on the V1 and neglect V2. And later we come back to the case with V2 potential. But for the moment, let me focus on the case with V1 potential. Okay. And also we assume post-inflationary initial condition. So we have two different kinds of cosmic strings, phi1 cosmic strings and phi2 cosmic strings. Okay. So they're cosmic strings, but they're different the strings.
Sorry,
Yes,
can I ask
please.
sorry, I couldn't understand the difference between V1 and V2.
A difference is that the V1 is much bigger than V2.
You mean the scale lambda is
Yes,
greater?
scale lambda is very different. Here we assume that lambda is much larger than lambda prime, so that for the moment we can neglect V2 potential. Or if we apply this system to the QCD axiom, lambda prime is set by the QCD scale, and capital lambda is some high energy scale scale.
Thank you.
Yeah, I have one naive question. So,
Yes.
so why the potential should be cosine like a phi1 plus phi2? Why not they separate?
What do you mean by separate?
So the we could do lambda 1 and cosine phi1 and lambda 2 cosine phi2, something like this.
That's also possible, and cosine phi1 corresponds to the choice of n2 equals 0. And yeah, if n2 equals 0 and n1 prime equals to 0, this is the case you mentioned.
Yeah, and my question is, if we have the QCD like this theta term, and the gluon will generate this dynamical generate the V1 potential. So why V1 potential include the cosine phi1 plus phi2? Why the potential is something like this?
For instance, if phi1 is coupled to, say, one PQ quark, I mean PQ, that suppose that two PQ quarks that are separately coupled to phi1 and phi2. They have their charge under different U1s and different, so they are coupled to separately to phi1 and phi2. In that case, the axion phi1 and phi2, some combination of phi1 and phi2 are coupled to, say, gluons or hidden gluons, whatever. So it is possible to have a situation where two axions are coupled to the same gauge field. In that case, some combination of phi1 and phi2 acquires potential like this.
Okay. Thank you.
Thank you for the question. And let me consider the case with V1 potential. Okay. And this is what I said basically. So here we have theta 1 and theta 2, and they both are 2 pi periodic. And it means that the vertical lines and these horizontal lines are identified with each other. Okay. And in the case of N1 equals 1 and N2 equals -2, the V1 potential is minimized along the red dashed line. So there's a flat direction, okay, along this red dotted line. Potential is flat. On the other hand, if you go this direction, orthogonal to the red line, the axion is heavy. And if you go this direction, you climb up the potential, and here is potential maximum, and you go down, and you here at the potential minimum again, and so on. So there's light axion, or in this case, the massless axion along the red dotted line, and heavy axion along the orthogonal direction. And we want to identify the light direction with the QCD axion. And as I mentioned, because we consider the post-inflationary scenario, there are two different kinds of cosmic strings, phi1 strings and phi2 strings. Okay, so let's consider phi1 string. Around phi1 string, phi2 is almost constant. Okay, and only phi1 changes. More specifically, as you go around the phi1 string, the angle theta1 changes by 2 pi, but theta2 doesn't change. Okay? On the other hand, if we go around the phi2 string, theta2 changes by 2 pi, but phi1 stays constant. Okay? This is the two different kinds of cosmic strings. And now we introduce the V1 potential. If you look at this potential, and suppose that we go around the phi1 strings as before, then the phi2 doesn't change. So you may simply take phi2 as a constant. And as you go around the potential, theta1 or phi1 over f1 changes by 2 pi. This part changes by 2 pi. And because we have n1 coefficient, it means that you go up and down the potential n1 times as you go around the phi1 cosmic string. It means that n1 domain walls appear, and all of them are attached to phi1 string, like this. Similarly, if you go around the phi2 strings, you see that n2 domain walls are attached to phi2 strings. And these two are the building blocks of the topological defects of this two axion system.
I have a question here.
Yes, please.
A little confusion that I'm currently having is that when people say about the domain wall problem, that usually refers to the presence of domain wall after the QCD crossover, after the axion gets massive, and that axion is not this n1 phi1 plus n2 phi2. Instead, it is n1 prime phi1 plus n2 phi2 n2 prime phi2. So it seems like the walls here in this slide doesn't seems to be that axion wall, axion domain wall, right?
You are right. So these domain walls are the domain walls of heavy axions, not the QCD axion. So their tension is much higher because, as I said, the lambda is assumed to be much higher than the QCD scale. So tension is very large. But this high tension here in this setup.
Please continue. Yeah.
Okay. If you have any questions, please interrupt me anytime. And
okay, thank you.
This phi1 strings and the phi2 strings and the domain walls attached to these the cosmic strings are the building blocks. Let us consider a simple case. Suppose that n1 equals 2 and n2 equals 1. Then what happens? Then because n1 equals 2, two domain walls are attached to phi1 string. And because n2 equals unity, one string is attached to phi2 string. So by combining one phi1 string and two phi2 strings, we can consider this kind of composite object, and which is termed as string bundle. Namely, so the string bundle consists of multiple strings, and they are connected by domain walls, stretching between the strings. And actually, this string bundle corresponds to the cosmic string of the light axion. Okay. As I said, this combination appearing in the cosine function is a heavy axion. The orthogonal direction is a massless axion. And this string bundle corresponds to the cosmic string of the light axion. And yeah, you can, if you calculate the change of the phases, you can easily show that this object corresponds to the ordinary cosmic strings. And we performed the numerical lattice simulations first on 2D, and this is the result. And each other side corresponds to 2 hyperhorizons. So at this in this snapshot, the lattice box this lattice contains 4 hyperhorizons. And you can see that indeed there are cosmic strings and connected by domain walls. String bundles are formed as shown here. So these are indeed string bundles that consist of 3 cosmic strings. And here some domain walls are still stretched between cosmic strings, but in Hubble time, the strings may disappear or may form a string bundle. So these objects are really formed in the numerical simulations. And this is a result of the 3D numerical lattice simulations. And you can see that the string bundles are being formed like this. And once string bundles are formed, this UV physics are really confined inside the cosmic strings of the QCD axion or massless axion, so that the subsequent evolution is completely the same. You cannot tell the difference from the ordinary cosmic strings. In this example, the details of UV physics is just confined inside the string core, and you don't have to care about the UV physics.
I have a question here as well. Like,
Yes, please.
I'm sorry, but okay. So here in this figure of the string, in the three-dimensional case, even though far from the string, it seems like each of the bundle acts like just a single cosmic string. But the fact that the string bundle is composed of multiple elementary strings actually makes them quite distinctive from the usual string in a sense that they can form like a multi-branched vertices. Like, I don't know if I'm conveying this idea correctly, but so for example, if you look at the left bottom part of this figure, then you can actually see that there are like 3 bundles connected all together, meeting all together at this. No, I'm sorry, the right bottom part.
Okay. This
So
one.
there we have like 3 string bundles connected to each other through this like a loop like it's not really a loop, like something similar to
Yeah.
the
So
gluon loop. Like yeah.
yeah, it is possible to have this kind of vertices that are not seen in the ordinary cosmic string for the moment. But if you further follow the evolution, we believe that these structure will disappear. They are actually unstable and will simply become the ordinary cosmic strings. So we believe that these structure are only temporary, and they will disappear very soon.
Okay. Thank you.
But you are right. We have to show numerically that this composite object indeed behave like ordinary cosmic strings, and we should actually we are planning to do that. First we have to check if this object really follows the scaling solution, and so on. And if there's a difference from the ordinary cosmic string, that would be interesting. But for the moment, at least for this simple case, that we expect the string network will gradually follow become the ordinary cosmic strings. But we don't know what happens if N1 and N2 are much larger.
Thank you very much.
Okay. And so let me go on.
Uh,
And
so-
what happened? Yes,
okay,
please.
sorry, so I couldn't understand this kind of string bundle configuration well. So in the previous slide, so you said if we focus on phi2 string, phi1, yeah, phi1 is like constant and vice versa.
Yes.
But if you look at this, please go to the next page. If you look at this kind of configuration, so let's say if we focus on the left phi2 string,
Mhm.
how phi1 field goes around the phi string.
Yeah. So yeah, thank you for the question. So say along the domain walls shown by this black line, the cosine function takes a value 1, no, -1, so that the V1 has a maximum, okay, because it has energy, and the
Yeah.
V1 takes a maximum value. So along this black line, the cosine function takes a value of -1. It means that this combination of phi1 and phi2 is equal to pi. Okay? And so if you cross this domain walls around the phi2 strings, indeed only phi2 changes and phi1 stays almost constant. But this combination gradually changes as you become closer, get closer to phi1 string. And around the phi1 string, only phi1 changes.
Okay, I see. I see. Thank you. Now I understand.
Thank you. So at least in this case, we observe the string bundles are formed and the subsequent evolution is exactly the same as the ordinary cosmic strings, if our expectation is correct. And so let me go on to a bit more complicated case where N2, N1 is same as before, but we increase N2 from 1 to 3. Then what happens? And as before, two domain walls are attached to phi1 strings, and now 3 domain walls are attached to phi2 strings. So as before, we could consider a string bundle that now consists of 2 phi2 strings and 3 phi1 strings. And they are connected by domain walls like this. And they are isolated cosmic strings. And as before, this corresponds to the ordinary cosmic strings. If you go around the string bundle, the massless, almost light axion changes by 2 pi, while the heavy axion remains constant if you go around this object. But because, the situation or network is a bit more complicated than before, instead of writing this, the field configuration, you could also write or draw this kind of a string wall network. Okay? Phi1 string and phi2 strings are connected to each other by domain walls, but they are not isolated. They rather they form a network, not isolated objects. So the question is, which is more generally found in the realistic cosmological evolution? And to see this, we need to perform the numerical lattice simulations. And this is the result of 2D. And you can see that instead of string bundles, we see the string wall network. And this is the 3D results. And we don't see any string bundles from the numerical simulations. Instead, we found that string wall network remains. So as there was a question, this domain walls is not the domain walls of the QCD axion, but this is heavy axion domain walls, and it has much larger tension than the QCD axion domain wall. So this is really cosmological problem. If you consider 2 PQ scalars and with this numeric coefficients, then consider also the post-inflation scenario for both PQ scalars, then we end up with string wall network. And this is a cosmological domain wall problem. So let me summarize what we found so far. If N1, either N1 or N2 equals unity, then domain walls can have an n. It's bounded by a single string, and string bundles are easily formed in this case, as we have seen in the first example. On the other hand, if n1 and n2 are greater than or equal to 2, then instead of forming string bundles, we found that string wall network remains. And in the first case, when string bundles are formed, the subsequent evolution is same as ordinary cosmic string, but in the other case, it's very different. Instead of strings, we are left with domain wall network, and this is nothing but cosmological domain wall problem. And also, anyway, we have to make domain wall network unstable and decay to be consistent with the standard cosmology. And at the decay of heavy domain walls, they produce large amount of gravitational waves because it has large tension. And in this paper, almost 10 years ago, we showed that if this decay occurs around the QCD phase transition or crossover, the large amount of gravitational waves are produced, and that can be probed by the pulsar timing array in this paper. Please go ahead, Kawana-san.
Sorry, so is this result essentially the same as the conventional domain wall problem? I mean,
No.
oh no.
In the conventional domain wall problem, the problem arises because there are physically distinct vacua, and they are populated with equal probability, and domain walls appear connecting different vacua, and the domain was stable. Domain was unstable and causes cosmological problem. Here, the situation is different. For instance, in the case of n1 equals 2 and n2 equals 3, the physical vacua is unique. Or more precisely, they're connected by massless degrees of freedom. And so in that sense, there's no distinct vacua. But still, we have the domain wall network like this.
Okay, I see.
So in some sense, even though the physical vacua is unique, we are left with domain walls simply because of combination of connecting domain walls and strings.
Thank you.
Yeah, or you could say that in the case of n1 equals 1, domain walls are bounded by just single string. Okay. And in the case of n1 or n2 greater than or equal to 2, you could bound the domain walls by a set of strings, not a single string, but some structure is needed. And because as I said, the vacuum is unique, you can go to the other side of domain walls continuously if you have appropriate boundary. But the problem is the required structure of this boundary is very complicated, so that the solution exists. But in the actual cosmological evolution, these boundaries are never formed. And this is the reason why domain walls remain in this case. And of course, if you consider large n1, especially if the greatest common divisor of n1 and n2 is greater than or equal to 2, then the situation is very similar to the ordinary domain walls, because in that case, we do have physically distinct vacua. So it is kind of trivial that we are left with domain walls. But the point is that point of this argument is that even if physically there's unique vacua, domain walls remain.
I see. Thank you.
Yeah, thank you for question. So let me go on. And so far we assume the post-influence scenarios for both phi 1 and phi 2. But because now we have multiple axions, we could choose mixed initial conditions. Namely, for instance, we could assume pre-inflationary condition for phi 1 and post-inflationary condition for phi 2. Then, because we assume pre-inflationary condition for phi 1, there's no phi 1 strings in the observable universe. They are simply inflated away due to inflation. And we only have phi 2 strings. then in this case, it is kind of trivial that string bundles are never formed because it requires certain number of phi1 strings. But because phi1 strings are inflated away, there are no phi1 strings. We have only phi2 strings in this case. Then the string wall network remains if the N2, the domain wall number of phi2 strings, is greater than or equal to 2. And this is the case even if N1 equals 1. If we assume post-inflationary scenarios for both PQ scalars, the string bundles are formed in this case, and there's no cosmological domain wall problem. But if we switch one of the initial condition from post to pre-inflationary condition, then we are left with domain walls. So if you switch the initial condition like this, the domain walls are more likely remain in this case. So that is the one example of mixed initial condition. And okay, let me go on to the case with V2. So far, we neglected the V2, but in order to give a mass to the light axiom, we need to introduce additional potential V2. And in this case, I'm going to say that induced domain walls are formed, but before proceeding, let me first explain what induced domain walls are. So to explain this, let me consider a simple setup. First, assume that the heavy axion phi has a domain wall like this. So this is in the real space. On the left side of domain walls, this phi field has a field value phi left, and on the right side, it is given by phi right. And the domain walls appear connecting these two different vacua like this. And let us couple phi to gluons like this. Then in the low energy, we can integrate out phi. Then phi field contributes to the theta parameter. So on the left side, theta parameter is theta left, and on the right side, theta parameter is theta right. So we have the strong CP problem, but the theta parameter is different in the different domains. And now the QCD axiom comes to rescue the situation. So we introduce QCD axiom A, similarly coupled to gluons like this. Then, as we know, whatever the theta parameter is, the axiom cancels the theta parameter so that the effective theta parameter vanishes in the vacuum. So axiom field takes a value minus theta left on the left side and takes the value minus theta right on the right side. So as you can see, the QCD axiom A has a different value on the left side and right side of domain walls of heavy axiom phi. It means that even if we start with spatially homogeneous QCD axiom, through the mixing induced by coupling to gluons, the domain wall-like structure is induced along the QCD axiom A, and it appears exactly where the heavy axiom domain walls exist. But because QCD axiom is much lighter than the heavy axiom, the width of induced domain wall is much thicker than that of heavy axiom domain wall. Okay, and this is the induced domain wall. So now we introduce V2 potential, and as I said, we introduce the V2, and the potential height is lambda prime, and they generically have different anomaly coefficients, N1 prime and N2 prime. And because phi1 and we have two axioms, phi1 and phi2, and two potentials, V1 and V2, so that both potentials can be minimized in any domains. So both cosine function takes a value of 1 in any domains. So there's no energy difference between the different vacua. All the vacua are degenerate in energy. No potential bias at a minimum. So in other words, so here we assume N1 equals 2. So phi1 strings have two domain walls. So it is sticking out like this. And if we turn on V2, then domain walls appear exactly at phi1 domain walls exist. And so V2 the domain walls appear around the V1 domain wall. So this is induced domain wall. And both sides are degenerating energy. Both vacuum are degenerating energy, thanks to the presence of induced domain walls. So this means that even if we include V2, the string wall network found found so far persists because there's no potential bias between different vacua, so they are stable. And so we still have domain wall problem even if we include V2 potential. Okay. So this is one of the important conclusion of our study. And in order to avoid the domain wall problem of this heavy axion, we need to introduce a potential bias along the heavy axion. If we do so, we can make domain wall network unstable, and while the PQ mechanism remains intact, because potential bias only give a mass to the heavy axions, not the light axion, if we choose potential bias along the heavy axion. And later I will also mention another solution. Okay, I don't have much time, so let me go quick. Let me give two cosmological applications. Okay, one is induced domain wall decay. As I said, when we consider heavy axion domain wall, and if it is coupled to gluon, the domain wall-like structure is induced for the QCD axion, even if you start with pre-inflationary condition for the QCD axion. And here we assume the post-inflationary condition for heavy axion, so that there's phi string and domain walls, but initially the QCD axion is spatially homogeneous. The model we considered is given by this, and the phi heavy axion has, in this example, a domain wall number equals 2. So along phi string, we have two phi1 up to phi domain walls. And because of this mixing between two axions, and so this part, the first potential comes from the QCD, and the induced domain walls appear along the phi domain walls. And it is much, the width is much thicker. Okay. And for simplicity, we assume hierarchy in the mass and the tension of domain walls, so that the dynamics of QCD axion or the induced domain walls do not affect the dynamics of the phi domain walls. And let me explain a bit more detail. So suppose that we have phi domain wall in the XY plane, like this, and the theta parameter is different for the negative z and positive z. And for negative z, the axial potential is like this. And for positive z, the axial potential, QCD axial potential is given by this blue lines. And their potential minima is different because the phi field takes a different values. Okay. And the induced domain walls appear connecting this vacuum and this vacuum. And please note that distance between the two vacua is generically smaller than 2 pi Fa. So the tension of the induced domain walls is generically smaller than that of the ordinary domain walls of the QCD axion. And this is the numerical calculation. And the orange line is this is almost step-like function. This is a phi domain wall. And this blue line is QCD axion induced domain wall. Okay. It appears where the phi domain walls exist, and it does width is much thicker than that of phi domain walls. Okay. And this figure shows where you can explain the all dark matter by the QCD axion generated by the decay of induced domain walls. Here we assume that we introduce potential bias along the phi direction, not a direction, because we do not want to spoil the peak mechanism. Then the heavy axion domain will decay at a temperature TDK, which is shown by this vertical axis. The horizontal axis is the decay constant of the QCD axion. If we go above this red orange line, the heavy domain walls decay before the QCD axion starts to oscillate. So induced domain walls do not appear if you are above this red line. So let me focus on the region below this line. And the green line represents the BBN bound. And this blue line represents the contribution coming from the ordinary misalignment mechanism for the QCD axion, explains all dark matter. So if you are left of the blue line, the ordinary misalignment mechanism cannot explain all dark matter because FA is small. But because we have now the extra contribution from the induced domain walls, okay, the heavy axion has the domain walls, and it induces the QCD axion domain walls. And when the heavy axion domain wall decay, the induced domain walls also disappear, producing QCD axion. And along the red line, you can explain all dark matter by the QCD axion generated by the decay of induced domain walls. And as you can see, the decay constant can be as low as 3 times 10 to the 9th GeV. Even for such a small FA, you can explain all dark matter if you consider this production mechanism. And this is the gravitational wave spectrum we calculated. The red line is the analytical estimate for this model parameters, and the blue lines are numerically obtained gravitational wave spectrum obtained in this paper. Actually, this gravitational wave spectrum is the first the result of the numerical simulations, including the potential bias. The analytical estimate is based on the numerical simulations, which does not include the potential bias, assuming the instantaneous decay of domain walls. But of course, it takes finite time for the domain wall network to decay, and it is crucial to include the potential bias in your numerical simulations to derive the realistic gravitational wave spectrum. And this was done in this paper for the first time. Anyway, for this model parameters, you can explain the nanograph hint for the stochastic gravitational waves in the nanohertz range, as shown here. And in the final 5 minutes or so, let me explain our new solution to the QCD axion domain wall problem. So far, the QCD axion was the lightest axion. All the other degrees of freedom are much heavier than the QCD axion. But here, let me focus on the other case, the opposite case. And as you know, in the DFSD axion model, the ordinary standard model quarks running in the loop to connect the axion to gluons. And because of the generation or number of quark flavors, domain wall number, NTW, is equal to either 3 or 6, depending on how the PQ scalar is coupled to the Higgs sector. Okay. So in the case of domain wall number equals 3, the 3 domain walls are attached to the axion string like this. Of course, even in the case with the axion model, if you have multiple set of PQ quarks, you similarly have a domain wall number greater than 1. And our proposal is like this. We introduce additional or massless axion coupled to gluons, which is denoted by this round phi. And for simplicity, phi does not have any other potential. Then the original phi is say you could consider case VZ like setup for phi field. So in some sense, this solution can be given by a combination of DFSD axion and case VZ axion. Okay, but we have 2 different axions, not a single one, but 2 different axions. And then what happens? We assume post-inflationary scenario for both A and phi. So in addition to A string, we also have phi strings. And because domain wall number of phi is assumed to be 1, the domain walls can have an n bounded by phi string like this. So, and string bundles are formed in this case instead of string wall network. In other words, domain wall network transitions to string bundles. And as I said, string bundles are nothing but ordinary cosmic strings corresponding to the light axion. So, and the cosmological impact of cosmic strings, it's much, much milder than the domain walls. The energy density of cosmic strings scale as h squared, hep-ph squared, if they are in the scaling solution. So they never dominate the universe. So they're much safer than the domain walls. So by changing the domain wall network to string bundles or just ordinary cosmic strings, we can solve the domain wall problem. The idea is just add light axion coupled to gluons. That's it. Then we can solve this long-standing domain wall problem of the QCD axion. And what is more is that in contrast to ordinary solution to the domain wall network, say introducing additional potential bias, in this case, strings or string bundles remain stable. Okay. In the usual case, we introduce potential bias, like extra peaky breaking term, then there's potential bias between the different vacua, so the domain walls feel pressure and they disappear. And at the same time, cosmic strings also disappear. And we are left with just axion waves that becomes cold dark matter. But here, cosmic strings, string bundles are stable objects. So they remain for a long time. And if phi's are really massless, we should, more precisely speaking, some combination of phi A remains massless, then these string bundles remain stable, and they should exist even in the present universe. And by the way, this
Sorry,
is
sorry.
yes.
In your model, sorry, one question. So in your model, then one of the axion becomes massless.
Yes, right.
You need to add additional term, like the V2 term, to make the axion massive.
Right. If you want to make the massless one massive, you need to add additional potential. That's right.
Then we lose the prediction of the axion mass and this decay constant. They have no relation.
It depends on how massive phi is, or the lighter axion is. Here, in order to solve the domain wall problem, we should assume the light axion is sufficient light. Because if you introduce additional potential for phi, the additional domain walls could appear, and they are attached to this phi string, and this revives the domain wall problem. In order to avoid domain wall problem or solve domain problem, the mass of the light axion should be sufficient light.
Okay, so the original, so the axion is really much lighter than the normal model predicted by the QCD axion. So
Well,
this axion is very light.
But the light axion is not the QCD axion. The heavy axion, I mean the combination appearing in front of a gluon, this combination is the QCD axion. The orthogonal direction does not couple to gluons, and they just remain, and they are massless.
Oh,
So
okay.
the prediction for the QCD axion mass and the decay constant, all these things are same as the ordinary case. But
Oh, yes. You have the similar axion like a QCD axion, but you have additional light axion particle, which is
right.
mass very small.
Yeah, exactly. So we have,
Okay.
in addition to QCD axion, we have extra axion-like particle. And in particular, if you consider combination DFSC axion plus case with the axion, this light axion has a coupling to photons, even if they are not coupled to gluons. So this can be searched for by observing CMB, for instance.
Okay, thank you.
Yeah, thank you. And so this is the 2D numerical simulations, and the domain network indeed end up with a bunch of string bundles like this. Sorry, it's difficult to see, but here I introduce the coupling of the light axion to photons. Then if the light axion is almost massless, this string bundles remain in the present universe, and if it is coupled to photons, the cosmic string loop can contribute to the, say, cosmic birefringence. The phenomena of that the polarized plane of CMB photon gets rotated when the CMB photon travels from that scattering surface to the observer. For instance, if it passes through the string loop, the polarized plane gets rotated by some degree. And this cosmic birefringence can be searched for by looking at the by using CMB polarization data. That's one possibility. And also, this string bundles have relatively large tension, so it could also affect the CMB temperature polarization fluctuations. And also, it emits the gravitational waves and can be constrained or also searched for by the pulsar timing arrays. Okay, so let me wrap up my talk. So we consider a topological defect in the multi-axion system, and the motivation is that simply we do not know we do not know anything about the PQ sector. And we considered a minimal extension, namely 2 PQ scalars. And we found that depending on the anomaly coefficients, we often are left with domain wall network instead of cosmic strings. So this drastically changes the cosmological evolution of the axion and topological defects. Now we gave the 2 examples. The one is the QCD Axion dark matter produced from the decay of induced domain walls, and the other is a new solution to the domain wall problem of the QCD Axion. And this has implication for, say, CMB cosmic birefringence and so on. So if we consider multiple axions, the cosmological evolution of topological defects are drastically modified. So in multi-axion system, the fate of topological defects are very different. So in that sense, you can say that more is different. Yeah, that's all. Thank you very much for your attention.
Thank you for the very nice talk. Are there any more questions?
If I may,
Please.
okay, I have a question about this, like exclusion plot that you have shown.
Yes,
Yes, here, yes. And here, like, according to my understanding, like there, the rho A decay is solely from the decay of the induced domain wall, right?
that's right.
And I wonder whether it should be also considered the fact that the dynamics of the heavy axion string, let's say, because the dynamics of the heavy axion domain wall there will also, because it will also steer the pre-inflationary A field there, because according to the very same dynamics that has developed the induced domain wall, the dynamics of the phi field will also steer the A field. So it will not be fixed at the initial value, which is pre-assigned from the pre-inflationary era, right?
So the heavy axion domain walls, of course, move around
Yes.
at the speed close to the speed of light, and the induced axion domain walls simply follow the dynamics of the heavy axion, because there's huge hierarchy between the two domain walls. Tension is different, masses are different. So induced domain walls simply follow the evolution of heavy axions, and when the heavy axion domain was annihilate, and we believe that only the heavy axions are produced and no light axions are produced. Light axion comes from the decay of induced domain walls because they are mass eigenstates. So, heavy axions and QCD axions are separately produced from the annihilation of heavy axion domain walls and the induced domain walls.
But then, wouldn't the dynamics of the heavy axion domain wall induce the perturbation or the fluctuations on the light axion field, which will actually be the radiation, which can be accumulated during the dynamics era, even before the decay of the heavy axion domain wall?
Well, so this can be considered as kind of scattering problem of the axions and the induced domain wall. Okay.
Yes.
And because mass is same on both sides of induced domain walls, actually axion quanta can simply propagate through the axion domain induced domain walls and nothing happens.
I see.
Because this is a
th-
vacuum solution in some sense.
okay,
If the
thank
mass
you.
is if the mass is different, they can be reflected and so on. The energy transfer could the induce axion waves as the domain walls move around. But in this case, mass is same and everything is smooth, so nothing happens.
But here the domain wall tension is actually larger than the axion mass here, because the domain wall tension here is actually mostly gonna coming from the heavy axion domain wall, not from the light axion induced domain wall, right?
But they are separate. They exist at the same place, but they are different field configuration. Okay, the light induced axion interact with the QCD axion or the light mass eigenstates. And if we want to consider the heavy axion dynamics, of course, heavy axions or heavy mass eigenstates interact with these heavy axion domain walls, but not with the induced domain walls. They're kind of orthogonal to each other in some sense.
Okay, thank you very much.
Thank you.
May I?
Yeah, please go ahead.
Okay, so could you go to the last part, the new solution to
Yes.
table? So I think it is essential to choose n equal 1 for 5 part,
Yeah,
right?
exactly. Yes, you are right.
So if you consider 2 or 3 or whatever, so it doesn't work.
It doesn't work. It doesn't work.
Okay, then the domain network just it's
Okay.
produced. Okay.
Yeah, right. So yes, this is a crucial assumption for this mechanism to work.
See.
If I may, actually, I have one very associated question.
Yes, please go ahead.
So here, if it was very crucial to have a phi field with domain number 1 here to solve the domain wall issue, then how the scenario become more generic or of more of merit compared to the scenario where we have just a single axion field with the domain number 1, where we don't have the domain wall problem.
The problem is that if you consider DFS axion, the Weibull number is known to be 3 or 6.
I see. So this one is to solve the domain wall problem in the FSD scenario.
Yeah, for instance, or
Okay.
of course you could consider case with the axion model with multiple PQ quarks. In that case, also the Weibull number is greater than 1. So, and of course, there are a couple of solutions. One solution is to make the Weibull number equal to unity by adding certain number of PQ quarks, certain couplings. Then you can always make the Weibull number equal to unity by introducing additional degrees of freedom. The other is to introduce the potential bias. Then this can be realized by introducing PQ breaking, express breaking of PQ symmetry. But this potentially spoil the PQ mechanism. So we have to fine tune the CP phase. So what I know is that these two are the solutions. There's also Lazaridis-Chaffee mechanism, which connects the two different vacua by the center symmetry of gauge symmetry or the global symmetry. And but basically this is same equivalent to making domain number equal to unity. So there are two
But
types.
then,
Yeah.
but then, as far as there's also like a objection of that solution. Well, not really objection, but the potential objection of the solution, which is based on the paper by Matt Riss, like in 2023, right? In case of the solution for domain wall problem using that ZN discrete symmetry gauge.
Yes. So can you say the objection again?
So that was like so in order to actually solve the domain wall problem by gauging that discrete ZN symmetry there, then it should be assured that we're gonna end up with the cosmic strings having just a single shifting in that ZN symmetry group. But
Yeah.
that it is not really necessarily need to be the case because not the gauge is not really a gauge string though. The string that we might end up with can be of a multiple shifting. Like for example, let's say if you consider like a Z5, then instead of having just a single Z string, which gives rise to just a single shifting in the vacuum, the 5 vacuum there, that instead of that, we can also end up with having like a Z cube string, for example, which shift the vector by 3 unity. Then it can also be a generator of the Z5 symmetry, but then with that Z cube string, if we end up with Z cube string, then the domain wall problem is not really directly be solved.
Yes, that's
Right.
the objection to the Lazarus shuffle mechanism, and it's fair to say that it's really not trivial to implement Lazarus shuffle mechanism in the realistic TFSE axion setup, and it tends to be really complicated. You introduce many degrees of freedom and many axions and so on.
I see. So far you believe this is the most generic solution for the domain wall problem, which can still apply on the DFSC model as well.
Yes, of course, I like this solution, but I don't say this is superior to the other solutions. This is another solution to the domain wall problem.
Thank you very much.
Hi, I have a simple question about your last statement on the cosmic birefringence using the string bundle. So
Yes.
can you distinguish this type of solution from other explanation? Or I mean, in
So,
terms of the string bundle or just the axion field, or I don't know how many other possible solutions there are, but can you distinguish, I mean, other than cosmic birefringence, can you distinguish one solution from the other?
so you mean solution to the domain wall problem?
Yeah.
Yeah, so one of the features of our solution is the existence of light axion. So in addition to the QCD axion, we expect the existence of lighter axion-like particle, and you could search for this light axions through the various types of the direct the search experiments or astrophysical observation and so on. So, and also we may have this stable cosmic strings of the light axion, and this can be searched for the CMB fluctuations and also gravitational waves because actually the tension of F5, the decay constant of light axion is determined or predicted by requiring that the QCD axion coming from this topological defect during bundle formation explains all dark matter. And in our paper, we show the range of the F5, and it is interesting. It is just below the CMB bound. I mean, bound coming from CMB fluctuations, and also it is marginally consistent with the the recent pulsar time array observations. And because this is global strings, but because tension is heavy, so their motion can also generate other gravitational waves. And so currently they satisfy all the observation bound. But if we increase the sensitivity of these experiments or observations, you could find the signature coming from this object.
Okay, thank you.
Thank you.
All right. Well, if there are no more questions, then let's thank the speaker again,
Thank you very much.
and hopefully you can visit us in person sometime.
Yes.
Thank you very much.
Thank you.
Bye bye.
Bye.